Welcome to today's lecture on TTT, CCT diagrams and hardenability test. TTT diagram stands for time temperature transformation diagram. It is also called isothermal transformation diagram. Purpose of an isothermal transformation diagram is to provide different steel structure that are transformed from austenite over a period of cooling time. It graphically describes the cooling rate required for transformation of austenite to perlite, bainite or martensite. TTT diagram also gives a temperature at which such a transformation takes place. Microstructural changes that occur in the solid when they are rapidly cooled in a liquid bath at the desired temperature below eutectite temperature for a certain period is called isothermal transformation in the solid state. Here you can see this iron carbide transformation diagram. So this is a eutectide temperature, solid temperature. So based on the this all austenitic region above this line austenitic region. So to get a different microstructure, how to do the cooling. For an example, if I want to have a perlite structure, then I have to cool very slowly to get a perlite. So based on the when you want to have a bainite, so you can cool up to some temperature. For an example, 500 degree. Then after that you can maintain that temperature. After that you can go like that. You based on the microstructure requirement, you can vary the cooling rate. So that is a very important. This is for that purpose. TTT diagram will tell you how to get a different microstructure by cooling. Okay, so that is the main purpose of this TTT diagram. Specimen is cooled rapidly, so that is 433 degree Kelvin and left for 20 minutes. The cooling rate is too rapid for perlite to form higher temperature. Therefore, steel remains austenitic phase until MS temperature is passed. So that means, so if we cool fast, here you can see that. So when you cool fast, so you will get a martensite. Here you can see that martensite start. So you cool very fast, and then after that maintain the temperature below this line. If you cool it, you will get martensite. So here, so it touches this bainite region, so you'll get some amount of bainite as well as martensite. So if it is 100% mass martensite, cooled rapidly below this probably around 150, then after that you maintain that temperature so that entire austenite is transformed into martensite. Like that, different cooling temperature we have to prepare and to get a different microstructure. Time temperature transformation diagram is a plot of temperature versus logarithm of time for steel alloy of definite composition. It is used to determine when transformation begin and end for an isothermal. Isothermal means constant temperature, heat treatment for previously austenized alloy. When austenite is cooled slowly to a temperature below lower critical temperature, the structure formed is perlite. As the cooling rate increases, perlite transformation temperature gets lower. The microstructure of material is significantly altered as the cooling rate increases. By heating and cooling a series of samples, history of austenite transformation may be recorded. So the difficulties in plotting TTT diagram during transformation of austenite to martensite or perlite, it is impossible to change the temperature from 727 degree to 500 degree in zero time, and from 500 to 0 degree. Specimens should be small in nature and care should be taken and special care should be taken during the rapid transfer between baths. The austenite to martensite transformation does not occur at the room temperature. and the material should be cooled below room temperature after transmission. These are all some of the difficulties in using a TTT diagram. Here you can see that different microstructure. So this is stable austenite. Above this austenite. So when you this is the temperature from which you want to get a different this microstructure. If you cool very slowly, so when it reaches this line, austenite start to transform into perlite. Then after that, slowly it get transformed, and so if you maintain this particular temperature for a longer period, you will get 100% perlite. So otherwise, if based on the cooling rate, so you may get perlite or bainite or martensite. So MS is martensite start, MF is martensite finish. So continuous cooling curve in all the practical application, so very difficult to maintain for a temperature for a longer period of time. So you have to cool fast to a certain temperature. Then after that, so you have to carry out this work fast. Then after that, you have to get the required microstructure. So continuous cooling diagram is a practical diagram. Here you can see how to get the how to do the cooling to get the required microstructure. How the austenite is transformed into fine perlite. Here you can see that. So up to this temperature, it cooled fast. After that, you maintain that temperature so that you get a fine perlite. Continuous cooling transformation phase diagram is often used when heat treating steel. These diagrams are used to represent which type of phase changes will occur in a material as it is cooled at different rates. So it differs from one alloy to another alloy. It is not same for all. So here for this particular alloy, this is the critical cooling rate. If you cool faster than this, then you have a say chance of getting molten. If you want to get a molten side, you have to cool faster than cooling rate should be faster. Otherwise, you may get in addition to molten side, you may get bainite or perlite or something like that. So hardenability of steel is defined as susceptibility of steel to hardening when quenched, and it's related to depth and the distribution of hardness. This is an important point to be noted. Hardenability is related to depth and distribution of hardness across a cross section. There are various factors which affect hardenability or austenite grain size, carbon content, alloying elements percentage. Germany end quench test is used to measure the hardenability of a steel, which is a measure of capacity of steel to harden in depth under given set of conditions. So Germany end quench test is conducted as per ASTM A255. There is a standard. We have to conduct a test according to this ASTM standard. Here you can see that sample. So whose dimensions are given. So first you heat the sample and place it in this stand. Then you cool it. So then after that you take the sample out. So you grind this portion. Then after that you measure the hardness. So this is distance from this quenched end. So the quenched end hardness is maximum. When it moves away from quenched end, then the hardness becomes less. So when you cool fast, then hardness is increased, then cooled slowly. Accordingly, hardness values are decreasing. These are all dimensions are standardized. So this is a standard specimen preparation for Germany end quench test. The Germany test data illustrates the effect of alloying and microstructure on the hardenability of steel. Thank you very much for your watching this video.